Today's lecture is on correlations and copulars. Let me give you an outline of today's talk. First of all, what will be important if we look from the perspective of a risk manager to the risk in an institution. Of course, it's not only the risk in individual assets that are on the balance sheet, but in particular, it's in the total portfolio context that the risk manager is concerned with losses. That means that we should not only look to assets individually and the way that they could move, but in particular also to the way that they could co-move. Because if, in a particular case, an event happens where an asset shows a negative return, then it would be very favorable when other assets in the same portfolio would make a change in the opposite direction. That would be a mitigating event. So the extent of co-movement may then even enlarge the risk that is available. If the co-movement is low, then we would talk about diversification. So we will talk about different co-movement, different ways of modeling co-movement, covariance matrices, correlation matrices, copulars. What they all have in common is that they are simple ways to summarize the way that different random variables move together. And I will look to a couple of schemes in which correlation or covariances could change over time. Well, the first case is in fact the unconditional case. That's where we say, well, we believe that covariance matrices or correlation matrices always are the same, no matter what time we are in. But afterwards, we go, say, similar as we did with volatility in an earlier chapter, an earlier lecture. We will look to updating schemes for covariance elements or for correlation elements, and we will apply similar updating schemes such as the Gauge 1-1 and the exponentially weighted moving average method that we discussed earlier for volatility. So the same will apply, same methods will apply to covariance elements. Then once we have discussed correlation and covariance as a way to co-move, we will move to copulars. And there is a good reason to do that, because correlation and covariance really look to linear relationships only. So they assume that the two variables that co-move, that they co-move in a linear way. Copulars allow you for a way to have a more advanced type of relationships. So then the co-movement not necessarily is linear, but could take all sorts of different relationships. So I will be brief on say what copulars actually are, and well, in particular, the reason why we look to copulars is because it's an important element in determining the capital requirements under the Basel II Accord. So how much capital does a bank need to set aside for its loan portfolio? There's a very neat formula that is put forward, and this formula includes copulars, as a matter of fact. So you get a short basis on copulars, and then we go more into detail into this Vasicek's loan portfolio model, where we apply the copula to determine the credit risk and then also the capital requirements for the loan portfolio of a bank or financial institution. And what we will do is we will end with some properties of the multivariate normal distribution. So if you also would like to generate scenarios for the multivariate normal distribution, how would you do that? So let's start with the basis, co-movements. Before we took the perspective of individual assets, now we are going to take the perspective of a portfolio. And if we are concerned or if we are interested in risk of a portfolio of assets, then it's of course the volatility of the individual assets that are important to measure the uncertainty. But on top of that, we also need to understand how the assets in that portfolio co-move together. Because if there is a large propensity of the assets to move in the same direction, then that's unfavorable from a portfolio perspective, because then if there is an asset that has a negative return and then more of the other assets also will have a negative return, that enlarges the total loss of the portfolio. So it's important to have a good idea of what the measure of co-movement is, so then afterwards we can manage it. Well, there are easy ways and there are advanced ways to represent co-movements. So the easiest ways are the usage of covariance and correlation. So the covariance, we will discuss it in a minute. It's simply a measure of linear relationship between two variables. And of course, if I have a portfolio with many assets, then I can, for each pair of assets, I can determine its linear relationship, which we then refer to as the covariance between these two variables. Then there is one further step that you could take from moving from covariance to correlations. A correlation is simply a standardized way to look to the co-movement, to the linear co-movement in a portfolio. And then you get a measure on a scale of -1 to +1, where -1 means perfect negative relationship, +1 means perfect positive relationship, and 0 means there is no linear relationship. And then there's all the sorts of values in between. So let's look to the formulas for covariance and correlation. I look to two random variables, variable x and variable y. X has a mean denoted with mu x and a standard deviation denoted with sigma x, which you have determined before. Y has a mean of mu y and a standard deviation of sigma y. And then if I look to observations for these random variables, realizations in the past, then I denote with xt, I denote the observation of that variable x at time t. And I assume that I have observations for time 1 until time capital T. Same for variable y. So yt is an observation, is a realization at time t of variable y. And I assume here that I have observations for time 1 until time capital T again. Now, how do you determine the covariance, the linear relationship between variable x and variable y? It's simply taking the d-meaned realizations. So I look to the realizations of x and the realizations of y. I subtract, in both cases, their means. So then I have d-meaned variables. And for each point in time, I multiply the two with each other. I sum them up, and then afterwards I divide by the number of time periods for which I had observations. So that provides me a covariance element, the covariance between two variables x and y. And if I have a larger portfolio, I repeat this exercise for each pair of assets in my portfolio, which then gives me a covariance matrix. Next thing that you could do is to determine the correlation. The correlation between two variables x and y simply follow as the covariance of these two variables, covariance x and y, and then you divide it by the volatility of variable x and the volatility of variable y. So both the standard deviations. If you do that, then you have a standardized measure. Correlation is a standardized measure between -1 and 1. And that's nice because then that gives you a basis to think about high correlation, which means high linear relationship, and low correlation, which means a low linear relationship. As said before, -1 then is a perfect negative relationship, +1 there's a perfect positive relationship. When the correlation is 0, then there is no linear relationship. And then any value between 0 and 1, there is to some extent a linear relationship, which is positive. Any value between 0 and -1, there is to some extent a negative linear relationship between the two variables. So it's a nice way to get a general idea to what extent there is a linear relationship between two variables. So then next, if we move to updating schemes, if we believe that that covariances and correlations are not constant over time, then what is important is to understand, well, what is the contribution of observations at a particular moment in time. So assume I look to observations at time t. Well, then the contribution to the covariance, the total covariance between the variable x and y is what I will denote with Vt, and that's simply the d-mean value for xt, for the observation of x at time t, so in excess of its expected value, of its mean, times the d-mean value of y at time t, which is then the observation of y in excess of its expected value of its mean value mu y. So this is one of these observations. Then if I look to a weighting scheme, so I look at time n to what I would then take as a covariance, I would look back to all historical observations that I have at my disposal. So which means at time n minus 1, time n minus 2, n minus 3, etc. So these contributions to the covariance are then denoted with Vn minus t, because I move in the past. So I go back to time Vn minus m. I have m observations. And I weigh them with a weight which is denoted Wn minus t. So the weight at time n minus t. Well, the simplest case is the unconditional covariance case, where I assume all the historical observations to be equally important. In that case, they all have equal weight. Given that I have m observations, then that weight would be 1 over m. And then I'm back in the case where simply the covariance that I provide at time n is equal to the unconditional covariance. I simply take the contribution at each moment in time, and I equally weight it with 1 over m. So more advanced ways of updating the covariance elements is similar to the Garchman one for volatility, but now for the covariance element, I take a constant omega plus an exposure to the contribution of the observations at time t minus 1, denoted with Vt minus 1. So there's the excess, there's the d-mean x times the d-mean y is in this Vt minus 1, and a sensitivity and exposure to the covariance as it was provided in the previous period, so the covariance at time t minus 1. So very similar to volatility updating. So there's a lot of academic literature on these type of models. If you look to practical application, so these methods are rarely used in practice, at least, well, I have never seen them being used in practice. There's also, in terms of estimating these models, there's a lot of additional constraints that you have to meet. So it's not an easy thing to get these models properly estimated on a highly frequent basis. Second way of updating the covariance element is by usage of the exponentially weighted moving average approach, same as we did with volatility updating. So then we say, well, we look to the observation that took place in the previous period, so the Vt minus 1, again, so that is the d-mean x times the d-mean y that's in there. And I weigh that with the value lambda. And then on top of that, I have the covariance as I determined it one period ago at time t minus 1, which I have at my disposal, and I weigh that with 1 minus lambda. So if I do this exponentially weighted moving average with a particular lambda, and for consistency purposes, I use the same lambda to do the updating of the individual volatilities of the variable x and the volatility of the variable y, then I get an updating scheme for the covariance. So the covariance can be different at each moment in time. The volatility for x can be different at each moment of time. So I denote that with sigma xt. And the volatility of y can be different at each moment of time. So I denote that with sigma yt. So in effect, what I'm going to do then to arrive at correlations that move over time, that are different each time. So I'm going to apply 3 updating schemes, one for the covariance, one for the volatility of x, one for the volatility of y. I use the same lambda to do the updating schemes. And if I do that, then I arrive at a correlation which is then different for each moment in time. So this consistency definition of using the same lambdas for the updating scheme, for the covariance, and for both the volatilities, it's an important one. The consistency condition in general for covariance matrix is that the matrix needs to be positive semi-definite. And really what that means is that if you would determine the eigenvalues of a covariance matrix, then all these eigenvalues need to be non-negative. So they need to be positive or zero. Otherwise, the matrix is, we cannot take the square root of the matrix, and it's difficult to generate, it's impossible to generate scenarios with these matrices. So, and that's also say why it's a more tedious task to do the multivariate gauge models. So where you say, I want covariance matrix to be modeled using gauge specifications, is that very often this consistency condition where you say, well, the resulting covariance matrix that I have then determined with the gauge model needs to be positive semi-definite, that's very often violated. So it's more difficult than simply just estimating the model, but on top of that, there is this important consistency condition that may be violated quite often. So that makes it a bit less attractive to use gauge models for correlation and covariance updating. Let's look to an example of using the exponentially weighted moving average for updating of the volatilities, updating of the covariance matrix, and then see what the resulting updated correlation is between two series. I look to, for illustration purposes, to a total return stock index, which is the S&P 500. So it's a representative for all equity in the US market. And I use the FTSE US Big Total Return Index, which is representative, which is sort of a proxy for bond returns on large firms in the US as well. I took monthly data, and for a period of, say, almost 20 years, from February 1999 until March 2019. And below you find a plot of the monthly returns. So the blue line gives the monthly returns for total returns for the S&P 500 index, so for the equity part, and the amber line, the orange line, for the FTSE US Big, so more say for the bond return line. And we see that the volatility of the blue line is higher than the volatility of the orange line. We also see that these volatilities, the returns are different in different time periods. So there is, this is likely an indication that volatility changes over time. And we also want to understand, so that's one step further, to what extent the two series co-move with each other, and whether this co-movement is changing over time. So we apply then the exponentially weighted moving average volatility updating on both the total return series, and we apply the same thing on the covariance element between the two series. And for ease sake, I simply use a lambda of 0.94. Once I've done that, and then I need to, once I'm going to do the volatility updating, I need to have a starting value of that series. And what I do is that I determine the unconditional volatilities and the unconditional covariance simply by taking the standard deviation over the entire series and by taking the covariance over the entire two series. And that's my starting value of the updating scheme. So that's where we start with the 1999. And then the blue line and the orange line show how the volatility updating applies for both series. So the blue line shows that volatility moves up initially, then goes down, then moves up again, and then goes down. That's for the S&P 500 volatility. And the orange line shows that there's far less movement in the bond return volatility. So there is a spike in 2009, say around the crisis, but then afterwards it's going to be more calm again. So definitely volatility is changing in both series over time, but there is a huger effect in the equity index than in the bond index. So we also have done this for the covariance between the two at each moment in time, which I've not plotted in this figure. Instead, what I've done is I've plotted the black line, which is then the covariance at each moment in time, divided by the volatilities of both series at each moment in time. So, which is then, in effect, in a way, it's the correlation between the two total return series at each moment in time. And what's interesting there is that we see that the correlation is not constant. So that also means that the extent that both series co-move changes over time. So you have to look here to the y-axis on the right-hand side. So that's the scaling is on the right-hand side. So we see that initially in periods like 2001, 2003, this correlation between the two series is even negative, minus 20%. Then it's for a certain moment it's close around zero. But then we see in the crisis, so 2009, we see that the correlation spikes at a value of almost 80%, 0.8, so a strong positive linear correlation. It remains high then for a while until 2011, and then it goes to lower values, but it starts to be more positive, around 30-40%. 2018, it's negative again at minus 25%, and then it goes up. So that's interesting, and it's also relevant to understand that this correlation is not always the same. It's moving over time. And in particular, what the correlation does, what you hope that the correlation provides you, so like in the early periods, 2001 until 2004-5, is that if there is a negative correlation between two series, it means that it's risk reducing. So if one series moves up, then the other series is likely to move down. So that means that, say, deviations, unfavorable deviations, are mitigated by opposite results in the other direction. And then exactly at the moment where you could use risk mitigation, so where you could use the diversification benefit, so that means that you would like to have low correlations exactly at those moments. So in the crisis 2009, we see that the correlation, the negative correlation between the two series is no longer there. Instead, we see that it spikes at 80%, so that exactly at that moment, the correlation is very positive and there is no risk mitigation between these series. So that's an interesting observation, an important observation if we do risk management, is that at moments where extreme events occur in the market, we see that where we normally would expect to hope on diversification elements in the portfolio, very often because of time variation in the correlation, exactly at these moments this diversification benefit is not there. So let's next look to Copulas, and I limit myself to briefly talk about Gaussian Copulas. Gaussian Copula really means is that Gaussian means normal distribution. Let's look to two random variable x and y, and I would be interested to represent the co-movement between these two variables x and y, and instead of modeling the relationship, the co-movement relationship between x and y directly, what I'm going to do is I'm first going to transform these x and y variables to other variables, to variables u1 and u2, and then I will model the co-movement between u1 and u2. So that's a nonlinear transformation that I will apply, which allows me to have a nonlinear relationships between variable x and y, which is much richer than simply the covariance and the correlation relationships which are linear. So how does it work? Let's denote G1 and G2. Let's introduce them as the cumulative distribution functions for x and for y respectively. And let's U1 and U2 be the standard cumulative normal distribution functions, which I also denote with capital N. So there is always, because cumulative normal distribution functions have values between 0 and 1, there's always a one-to-one mapping from one cumulative distribution function to the other one. So I could simply say, well, if I want to transform an x variable into a u1 variable, what I do is I take the cumulative normal distribution function of x and I set it equal to the cumulative, I take the cumulative distribution function of x and I set it equal to the cumulative distribution function of u1, which is the cumulative normal distribution function. And then if I want them to rewrite it, then it's simply I take the inverse of the cumulative normal distribution function, that's the n inverse, of the g1x. So that gives me the u1. Same I do with the variable y. Its cumulative distribution function is denoted with g2. I set the cumulative distribution function of y equal to the cumulative distribution function of u2, which is the cumulative normal distribution function denoted with n. I take the inverse of that cumulative normal distribution function, so that's the n inverse of g2y, and I have the variable u2. So now I've first transformed the variables x and y to the variables u1 and u2, and it's only on the variables u1 and u2 that I'm going to impose a relationship. And simply what I do is I assume that this relationship is linear. So I assume that variables u1 and u2 have a bivariate normal distribution function. Given that it's linear between u1 and u2, and given that there is a nonlinear relationship to x and y, this type of transformation allows for more general relationships between the variables x and y. So it's an easy way to incorporate that. So I will not go in further detail on what Gaussian copulas actually entail. Instead, so this is simply the basis that you require to build up to the model, to the Vasicek model that's used for capital requirements calculation for loan portfolios of banks. And the second element that I need to get there, to get to the Vasicek model, is a factor model. Very simply because if I look to a portfolio of a bank, then very quickly such a portfolio has over a million contracts, over a million assets. So then if I need to measure the co-movement between all these assets, so I get to very large matrices, and so I need, which then even say becomes intractable to handle. So if I have capital N assets, and I look to the covariance matrix that's there, so then I need n times 1, n minus 1 times half correlations to determine which is a mess. So instead, what we will propose is that we could impose a factor model. And what the factor model simply does, it says, well, I'm not going to determine the co-movements between two assets directly, but this co-movement flows through a joint relationship that these two assets or any two assets have to a common factor. So what we will do, we will say, well, there is a common factor. Think of a macroeconomic variable or a market variable and say, well, if I know what the relationship is of each individual asset to that factor, then it's because of this factor that is moving that both assets will co-move. So that's a more parsimonious way in identifying co-movements in a portfolio, and it works pretty well. And also, so this factor model is the basis for everything that we do with credit risk capital requirements in Basel II. So this is the basis for the Vasicek model. So what we will do in a way, we will then take the Gaussian copula that we just discussed and apply it to a factor model to get to these capital requirements. Let's see how the factor model works. If we look to an individual asset, then we make the assumption that this individual asset has two sources of uncertainty. The first source of uncertainty is a common component, so something that is affecting not only this asset on a standalone basis, but it's affecting all assets in the world, all assets in the market. So that's a common effect. And next to that, there is a second source of uncertainty, and that's specific for this asset only. And because it's specific for this asset only, and it has no effect on other assets, we call it an idiosyncratic effect. So let this total uncertainty be denoted with UI. So the uncertainty for asset I is denoted with UI, and then it's a weighted average of the two sources of uncertainty. So there is capital F, which is then the common factor, and the AI says, well, what is the sensitivity of asset I to this common factor? So if this AI is high, then it's more sensitive to the common factor, and therefore it likely also has higher co-movement with other assets in the market that then also have, say, sensitivity for this common factor. And the second element there, it's the ZI, which is the idiosyncratic effect. So there is a subscript I because it's specific for asset I only, and it has no effect on any other assets. So it's the idiosyncratic component, and the weight that we put in front of that is the square root of 1 minus AI squared. And the reason why we take the specific weight is because if you then take the squares of both weights, then they exactly add up to 1. And that's a nice property to make the calculations convenient. We work in a standardized environment, which says is that the factors and the idiosyncratic shocks are all independent of each other, and they all follow a standardized normal distribution function. So that means that they have a mean 0 and a standard deviation of 1. So this AI is an important element in this specification, because in a way it says, well, to what extent suffers this asset I from co-movements with the market, and also then with co-movements with other assets in the portfolio. So an asset which has a low AI is convenient for a bank because there's only idiosyncratic risk here there, so from-specific risk. So there is no joint movement that may occur from this asset together with other assets. So from a portfolio perspective, this asset is uncorrelated then with the other assets, which is convenient. So more formally, if you would have to determine the correlation between two assets in the portfolio, then it means that you have to look to the correlation between UI and UJ. Given the fact that the variables all have mean 0 and standard deviation 1, it very easily follows that this correlation is simply the product of the two sensitivities for the factor. So the AI times the AJ, where AI is the sensitivity for the common factor for asset I, and AJ is the sensitivity for the common factor for asset J. So everything is standard normal, including the total uncertainty effect. And then next the question is, well, how could you apply this for a loan portfolio? So I start with a portfolio of loans, let's say it's 1 million loans, and for each loan, which is denoted with loan I at least know what its individual probability of default is. So PDI is the probability of default of asset I. This is something that a bank is required to determine for each individual asset in its portfolio. And so you could think of this as the result of an S&P rating for a firm, or when it's very small firms that do not have an S&P rating, it's simply a probability of default that is the result of internal credit scoring at a bank. So there are huge departments right now at financial institutions that do credit scoring of each individual asset in the portfolio. So the PD is known. Then what we do know is that because the UI is a standardized variable, normal distribution function, we know that with a PD of I, we could say, well, a default of asset I is the same as this standardized normal distribution variable. So this, the uncertainty, the total uncertainty for asset I, denoted with UI. So if this UI drops below the normal inverse of evaluated in this PDI, then this normal inverse PDI is exactly the threshold where we say, well, if we have worse values for UI that arrive, then it's a default. And if the value is better than this threshold of norms inverse PDI, then it's not a default. So what we have done is we have used this, this UI variable to determine a threshold, which then says as well, I could very easily say express defaults and non-defaults of individual assets in terms of evaluations of UI. Let's see why this threshold of norms inverse PDI is exactly the right threshold for a default to occur. Well, I look to the probability of UI being below the norms inverse PDI. Well, because the UI is normally distributed, standard normally distributed, I need to evaluate this norms inverse PDI exactly in the normal distribution function. So I take the normal distribution function of the normal inverse of the PDI, which gives me the PDI, so it's correct. So that then provides me at least, well, with the individual probability of defaults of each asset, and I also know what the thresholds are for the different measures of uncertainty, the UI and the UJs. So that's both are in default if they drop below the norms inverse of their respective PDs. And because I have modeled these UIs and these UJs and all other U's with a vector model, also I know what the co-movement is of these UIs and UJs. And that means that I also can then determine what the joint probability of default is because I know the correlation between the UI and the UJ. And that's important because if I look to risk of the bank, to joint credit risk, contracts going jointly into default, I need to know when do the cases occur that both UI and UJ and UK and all other U's, that they drop below their threshold of the norms inverse of their respective PDs. So let's see what could happen if I look to a worst case event that could occur. So I have to start with the UI, which is then the total uncertainty, total risk of asset I, which is a combination of a sensitivity for the common factor F and a sensitivity for the idiosyncratic component of asset I, the ZI. And now I want to understand, well, what is the effect of a worst case shock to the common factor? So I'm going to look to an event in F that only happens once every 1,000 years. So I put the critical value or the probability at 0.1%. So that's a very negative shock occurring to the common factor. So conditional upon this shock occurring, what's then the probability of the asset I going into default? Well, the probability of asset I going into default is the probability that UI drops below its threshold, and its threshold is exactly the normal inverse in the PDI, under the condition that there is this shock in F. So then next what I do is I substitute for the UI, I substitute the vector model, which is AI times the vector, but the vector is then this negative shock of normal inverse 0.001, so a very extreme shock, plus the idiosyncratic effect, the Zi. And this then needs to be, in order to go into default, needs to be falling below its threshold. Well, then the only source of uncertainty that is remaining, so the only random variable that is remaining in this expression is the Z. So I bring that to the left-hand side and all the other variables to the right-hand side, which means that I need to subtract, so I need to bring AI times the normal inverse. I need to bring it to the right-hand side, and then I need to divide by the square root of 1 minus AI squared. And then if I do that, then there is one last thing that I will do, is I will switch the sign, the negative sign in front of the AI. I will switch it in a positive sign, and then the critical value of 0.001 switches then in 0.999. So that's going from the left tail of the normal distribution function to the right tail. The probability mass is the same. It's only, say, with a different critical value, and I need to put a minus sign in front. So that's why the minus changes in the plus. And then, so what this expression actually is, it's the probability that asset I goes into default under the condition that there is a negative shock, negative common shock occurring to all assets. And then the question is, well, what is then the probability of default if we know that this shock occurs? And we call that the worst case default rate, WCDR. And so the certainty level at which we apply that is 99.9%, so that's the X. And then it's calculated using the cumulative standard normal distribution function. In there is the inverse of the cumulative normal standard distribution function evaluated in the PD. There is a sensitivity for the common factor of asset I. There's the normal inverse in that very certain probability of 0.999, and you divide by the square root of 1 minus the sensitivity factor. And this worst case default rate could be applied to see, well, how much capital do I need to set aside? Because capital you set aside for unexpected events. So, and then what we say is, well, let's look to the loan amount that comes with this asset I, which is denoted with L. If the asset goes into default, it normally doesn't mean that you lose everything of the asset, but there's always a recovery rate. So then the real loss is 1 minus the recovery rate times the loss that occurs. And of course, we need to know what the expected loss is when this occurs. And that's why we apply the worst case default rate. So we multiply the loan amount times the loss rate, 1 minus the recovery rate, times this worst case default rate to see, well, what's actually the value that is at risk. And we are then 99.9% certain. So I did a simple calculation for that. So we look to a loan amount of 100, a recovery rate of 60%, the probability of default in general, which then arises from a rating agency, is 2% for this loan. The sensitivity for the common factor is this 0.316228. And we look at certainty levels of 99.9%. So that means that this bank has high standards for its capital adequacy. So what's the worst case default rate at the 99.9%? Well, we need to determine the normal inverse at 2% at the PD. We need to determine the normal inverse at 99.9%. So there's lookup tables for that. And then we need to fill in the sensitivity for the common factor, A, both in the numerator and the denominator. All of that you evaluate then again in the cumulative standard normal distribution function, and the outcome of that is 12.8%. So let's think for a moment what this 12.8% actually means. It means that in normal circumstances, the probability of default of this asset is 2%, but if the factor really gets a very negative shock, something that would only happen very rarely, so only in 0.1% of the cases that would happen, then actually the probability of default is not 2%, but is 12.8%. So it's for this 12.8% probability of default, the worst case default rate, that the bank needs to put a buffer aside, a capital requirement. And so we then also say the value at risk, 99.9%, is then the loan amount, 100, times the 1 minus the recovery rate, so what's actually the loss rate then, 40%, times this worst case default rate of 12.8%. So that means that the bank needs to put on a loan of 100, needs to put 5.13 aside. And in the table below there are further details of the components that you need to calculate. Then let's look to the last part of today's lecture. Suppose that I have a multivariate normal distribution function, then it would be very convenient if I could also draw from this normal multivariate normal distribution function to generate many possible scenarios in the future, because that could give me a good idea of what kind of realizations could occur. And the question is, well, how do you do that? How do you draw from a multivariate normal distribution function? Well, let's first introduce notation. So vector x is an n by 1 vector of random variables that are jointly multivariate normally distributed. So they have a mean vector denoted with mu, where each element is the expected value of each element in the x vector. And they have a covariance matrix which is denoted with sigma. So if this is an n by 1 vector of random variables, then also the mean is n by 1, and the covariance matrix, of course, is n by n. So now there are a couple of technical steps that I need to take. First of all, what I need to do is I need to find the matrix P, which is a lower triangular matrix, and this matrix P has a very important property. So if I multiply this matrix P with its transpose, so I do P times P transpose, then it's equal to the matrix sigma. So if you want to determine this matrix P, then you apply what is called the Cholesky decomposition. And I have an example a little bit later of how that works for a small matrix. So first thing you need to do is determine the Cholesky decomposition of this matrix sigma. Then if you have done that, then the matrix X, the multivariate normally distributed matrix X, which has a mean mu and a covariance matrix sigma, can be rewritten as the vector mu plus P times epsilon. And this epsilon is now also multivariate normal, but has mean 0 and has only a diagonal with all variance and all standard deviations being equal to 1. So it's the identity matrix. And that's very convenient because it's easier to make drawings from epsilon than to make drawings from x. So each element of epsilon, in fact, is a univariate standard normally distributed variable. So I denoted that with epsilon I, which is then is one drawing. It's normally distributed with 0, 1. And there it's very easy to get drawings from a standard univariate normal distribution variable, because basically every statistical software package has standard routines for that. And even if you would go to Excel, then simply the code is norms, inverse, and then rand, where rand is a uniform drawing, and norms inverse then transforms that uniform drawing between 0 and 1 to a drawing of the standard normal distribution function. So there are a couple of steps then to take to do that. So you need the Cholesky decomposition, and then you need to do the drawing of the univariate normal distribution function, and you do it a couple of times. Once you've done that, then you multiply the drawing of the individuals, you put them in epsilon, you multiply them with P, and you add the mu, and then you have a drawing for x. So This Koleski decomposition, it's also something that many statistical software packages have as standard routines in there. Just to give you a flavor of how this works, so I put here a 3x3 example where the sigma 11, sigma 12, sigma 13, and so on are the elements in a 3x3 covariance matrix. And then the matrix P is a lower triangular matrix that if I multiply it with its transpose should give the covariance matrix. So I do lower triangular matrix means that on the upper triangular there are zeros, and I introduce P11, P21, P31, P22, P32, and P33 as the elements in the lower triangular part of this P matrix. So I need to multiply it with its transpose, and if I do all the multiplications and I try to arrive then at the values for this for all these P's, then well, the first element P11 is very easily found because I do P11 times P11 should be equal to sigma 11, so P11 is equal to the square root of sigma 11. Once I have P11, it's easy to determine P21 because I simply take the covariance element 21 and I divide it by P11. And then in the third element in the first column of the P matrix, the P31, it's simply the covariance element 31 and I divide it again by the P11. So you work column by column through this matrix and then only for the relevant non-zero P elements in the matrix. So then on the second line, the value for P22. So I take sigma 22 and I subtract first from that the P21 squared. And then I take the square root of that and I have the P22 value. So again, I use the information that I already had in terms of elements of P to get new P values, and I work through the matrix by column. So then the next element in the column is P32. I take the sigma element, sigma 32. I subtract the P21 times P31, and then I divide it by P22. And then I have all the elements in the second column. Then for the third column, there's only one element remaining, the P33. And what I need to do is I need to take the sigma 33 element, and I need to subtract the P31 square minus the P32 square, take the square root of that, and then I have the P33 element. So then I put all these values in that lower triangular matrix P, and that's the matrix that I apply so that I'm used to multiply the drawings from the standard univariate normal distribution functions. So this is an iterative process. If you do this for larger matrices, then of course it's easy to generalize it. So you work column by column. It's just the formulas get a little bit bigger, but it's easy to build it in as a routine. One important remark also here, what we already mentioned earlier, this matrix sigma. So if you want to do the Koleski decomposition, it needs to be positive semi-definite. So its eigenvalues need to be non-negative. So if that's not the case, then you see a couple of square roots that are taken in the formulas. Then what will happen is that I need to take a square root of a negative number, which of course is not possible. And that's also then the reason why I cannot do this Koleski decomposition. This concludes today's lecture on correlations and covariances and copulas on co-movements, basically. Thank you for your attention.